So, the last property of directional derivative, that is the chain rule of directional derivative, which we saw in the previous slide, is now explored in more detail because it is not very easy to interpret. Okay. So, consider this statement given by equation 25. Okay. So, the quantity G evaluated at x 0 plus u, and when expanded using Taylor series can be written as the quantity evaluated at x 0 plus the directional derivative of quantity G at x 0 in the direction u. Okay. So, now our given function is G equal to G 1, and G 1 is a function of G 2 and G 2 is a function of x. This is shown by equation 26. Okay. So, now using equation 25 for G 2, okay, we can write G 2. Okay. So, G 2 is x 0 plus u. Okay. We want to get the directional derivative of G at x 0 plus u. So, using equation 25 for G 2, okay, we see G 2 is G 2 x 0 plus directional derivative of G 2 at x 0 plus u. Okay. Therefore, substituting this expression over here. Okay. So, this was nothing but G 2, okay, x 0 plus u. Okay. So, this is the Taylor series expansion of G 2. Now, you can imagine, okay, G 2 as say another vector, is another vector, and this term over here is the direction. Okay. So, now if you have to do the Taylor series expansion of G 1 in the at the point G 2, okay, in the direction given by this second term. Okay. So, that would be, okay. So, it means you have to linearize G 1 at G 2 x 0, okay, in the direction of G 2 evaluated at x 0 in the direction u. Okay. That is the directional derivative of G 2 in the direction u. Okay. So, when you do this, what do you get? G 1 evaluated at G 2, okay, plus the directional derivative of G 1 evaluated at G 2 x 0 in the direction of the directional derivative of G 2. Okay. Okay. So, now you can see if G is G 1 G 2 x. Okay. Now, I am putting only one under bar because I just want to show that this is not a scalar. I mean, need not be a scalar, it can be vector, tensor, whatever. Okay. So, the directional derivative of this quantity G over here, okay, which is given by G 1 function of G 2 function of x, is nearly G 1, okay, evaluated at the point G 2, okay, x 0, okay, then plus the directional derivative of G 1 at G 2 x 0 in the direction of the directional derivative of G 2 at x 0 in the direction u. Okay. So, that is what our this statement, okay, that was our last property, equation number 24. That is what this means. Okay. So, equation 24, this is your directional derivative, and therefore, okay, therefore, you can see this is nothing but your directional derivative of G evaluated at x 0 in the direction u. Okay. That is how that property equation 24 actually came. Okay. So, you can understand what this quantity actually means. Okay. So, next we move to one example. Okay. We look actually two examples of application of directional derivative. Okay. So, the first one is pretty simple. Okay. We just take the concept of directional derivative and we try to derive the equilibrium equation for the system as which is shown here. Okay. So, here what you have? You have two springs which are connected in series. Okay. So, the spring stiffness of the first spring, okay, this is the first spring, this is the second spring, is K, and the stiffness of the spring 2 is also K. Okay. At point 2, you have an external force which is applied, okay, and say let x1, x2 are the displacement or the coordinates of points 1 and 2 after the equilibrium is achieved. Okay. Now, we want to derive the equilibrium equation for this system, okay, using the concept of directional derivative. Okay. So, the first thing we have to do is we write the total potential energy of the system. Okay. Now, the total potential energy of the system at equilibrium will be the potential energy of spring 1, okay, at equilibrium position, plus potential energy of spring 2, okay, minus the work done by the external forces. Okay. What are the expression for the potential energy for spring 1, spring 2 and the external work done? Okay. So, that we have to see next. So, remember x0 is a vector which is x1, x2, okay. It is x1, x2. Okay. So, this is not a nonlinear system, this is just a linear system, but to show that how directional derivative can be used to get the equilibrium equation, we have taken up this example. Okay. Next, the expression for the potential energy for the spring 1 will be nothing but half k x square, where x is the displacement of spring 1. Okay. So, what is the displacement of spring 1? It is x1 minus this displacement at this point. Okay. Now, this is a fixed end. So, it does not get any displacement, the spring does not have any displacement at this point. So, the potential energy of the spring will be half k x1 square. Now, the potential energy of spring 2 will be half k and the displacement square. Okay. So, the displacement of spring 2 will be x2 minus x1. Okay. So, you have half k x2 minus x1 the whole square, and the work done by the external forces will be F into x2. Okay. So, now you can substitute, okay, equation 31 in equation number 30 and you can get the explicit expression for the potential energy of the system. Okay. Now, you consider an increment in x. Okay. Now, from the equilibrium point there is a displacement u, okay, where u is given by u1 u2 transpose. Okay. It is a vector. So, now from the equilibrium position, now if there is a displacement u, what will be now the change in the potential energy of the system? So, what has happened? From x you have gone to x plus u. Okay. Now, the total potential energy of the system will be evaluated at x0 plus u. Okay. So, you have potential energy of the system at x0 plus u, the new point will be is the potential energy of spring 1 at the new point plus potential energy of spring 2 at the new point minus the work done, okay, to get to the new point by the external forces. Okay. Therefore, you can get the expression for the potential energy of spring 1 as half k x1 plus u1 whole square. Okay. So, if you see this expression over here, this is nothing but x1 x2 plus u1 u2. So, the resulting expression would be x1 plus u1 x2 plus u2. Okay. So, in your previous expression for potential energy, you just have to replace x1 by x1 plus u1 and x2 by x2 plus u2, and the potential energy for spring 1 will be half k x1 plus u1 the whole square plus half k x2 plus u2 minus x1 minus u1 the whole square, and the work done by the external forces is F external into x2 plus u2. Okay. So, now you can expand the potential energy at the current position using Taylor series, and that is what you get. Okay. So, the potential energy at the current position x 0 plus u will be nearly equal to potential energy at x 0 plus the directional derivative of the potential energy at x 0 in the direction u. Okay. Therefore, you can use the concept of directional derivative, okay, and this is the expression how you compute the directional derivative. It is given by d by d eta at eta equal to 0 pi of x 0 plus eta u. Okay. So, here to compute this expression, x 1 has to be replaced by x 1 plus eta u 1 and x 2 has to be replaced by x 2 plus eta u 2. Okay. So, if you do this, you can compute the directional derivative. Okay. Let us see what do we get. Okay. So, that is what you get. You replace x 1 by x 1 plus eta u 1, x 2 plus eta u 2, okay, and then this is the expression for the potential energy. Okay. That is what you get. And now it is very simple. You take the first take the derivative of this expression with respect to eta, okay, and then you substitute eta equal to 0. Okay. So, this I leave it to you. If you do this, what you will find? You will find that the directional derivative of the total potential energy of the system at point x 0 in the direction u will be k x 1 u 1 plus k x 2 minus x 1 into u 2 minus u 1 minus f u 2. Okay. Now, this expression, okay, can be written in a matrix form. It can be put in a matrix vector multiplication form as u transpose bracket, okay, k x 0 minus f, where k is called the tangent matrix and f is called the external load vector, and equation 39 gives you the expression for the tangent matrix and the force vector. Okay. So, that is what you get for the value of directional derivative of the potential energy computed at x 0, okay, in the direction u. Okay. Now, you note that the directional derivative which is given by equation number 38, this equation, okay, is linear in u, okay, whereas if you see the potential energy function which was given by equation 30, it is a nonlinear function in x. Okay. So, in this way we can say that we have linearized the potential energy function with respect to u. Okay. So, this point you note, equation 38 is linear in u. Okay. So, now the structure will attain equilibrium when the total potential energy becomes stationary. Okay. That is, the gradient of the total potential energy vanishes in any direction u. This means that the directional derivative should be equal to 0 at point x 0 in any direction u. For all directions u, the directional derivative of the total potential energy evaluated at the equilibrium position should be equal to 0. Okay. So, now if you see equation number 38 and now if you substitute this equal to 0, what do you see? U is an arbitrary direction, I mean it was up to us. So, if U transpose k minus k x 0 minus f has to be equal to 0. What does it mean? That k x 0 should be equal to f, okay, and this is your equilibrium equation. Okay. This is your equilibrium equation. Okay. So, you see here how the concept of directional derivative has helped us in deriving the equilibrium equation for the two spring system under the action of one external force with equal spring stiffness. Okay. And the final expression is given by equation number 40. Okay. So, now in actual practical application, this external force over here, okay, this will not be applied in one shot. Okay. What you will do is the total force will be a high magnitude. So, it will be split into smaller loads. Okay. So, this total load F will be applied in increments, okay, which means F will be summation from I equal to 1 to n delta F I. Okay. So, you will have F equal to delta F 1 plus delta F 2 all the way up to delta F n, where n is called the number of load steps. Okay. N is called the number of load steps. Okay. So, this is also called the incremental approach. Okay. Next, we look into the application of directional derivative to the solution of a system of nonlinear algebraic equations. That is what we are going to get in nonlinear finite element method. Okay. Displacement based nonlinear finite element method. Okay. So, consider you have a set of nonlinear algebraic equations which is given by equation number 41, okay, where f is a vector function, okay, f is a function of another vector x, where f is f1 comma f2 comma f3 all the way up to fn. Okay. So, there are n such functions. Okay. So, explicitly, okay, these equation 41 can be written as n such equations. Okay. f1 which is a function of x1 all the way up to xn equal to 0, f2 function of x1 to xn all the way equal to 0, like this. The last equation is fn which is a function of x1 x2 all the way up to xn equal to 0. Okay. So, where the vector x is expressed as x1 x2 x3 all the way up to xn. So, there are n unknowns. Okay. We have n equations, we have n unknowns, and these are nonlinear algebraic equations. So, that is what our aim is. We want to find the solution of equation number 41. Okay. Now, let us say this solution is given by x 0. Okay. So, how do we approach? Okay. So, what we do is we take the Taylor series expansion of the function, okay, like similar, and we look into the directional derivative of our function at solution point x 0 in any general direction u, which is given here, okay, and then the directional derivative of f evaluated at the solution point x 0 in the direction u will be d by d eta of f evaluated at x 0 plus eta u at eta equal to 0. Okay. So, now can we simplify equation 43 for our given set of nonlinear algebraic equations? So, let us see how you can do that. Okay. So, the first we can write the expression for directional derivative, and then this f over here is nothing but what is given by equation number 42 in the previous slides. Okay. So, you have these n equations. Okay. So, using chain rule you can write. Okay. So, you can chain rule, you can write summation over I equal to 1 to n del f by del x I evaluated at the equilibrium, okay, or at the solution point into d by d eta of x 0 plus eta u I. Okay. This evaluated at eta 0. This is here using chain rule, okay, because f depends on x 0 plus eta u. Okay. So, you can write this as d by d eta of eta equal to 0. To look it more closely, let us say this is x, okay, where x is x 0 plus eta u. So, f is a function of x and x is a function of eta. So, if you have to take del f by del eta, it would be del f by del x into del x by del eta. Okay. That is what we have done in the second step. Now, here if you see this expression, the first term is independent of eta, okay, and the second term only has eta. So, if you take this derivative, you only get u I. Okay. So, from the second term you only get u I. Eta equal to 0 have no meaning here, because once you take the derivative with respect to eta, there is no eta left into the final expression. Okay. So, then what do you get? You get summation del f by del x I into u I. This you can write as a matrix K evaluated at x 0 into a vector u. Okay. So, this term over here. Okay. So, this term over here is nothing but your matrix K, and the second term over here is nothing but your vector u. Okay. Now, this matrix K is also called the tangent matrix. Okay. So, in traditional linear finite element, sometimes the term stiffness matrix is used, but in the context of nonlinear finite element or nonlinear algebraic equation, it is the term tangent matrix which is commonly used. Okay. Now, what is K? Okay. K is the first row, if you see, is del f 1 by del x 1, okay. Second is del f 1 by del x 2 all the way up to del f 1 by del x n. So, this is your first row. The second row is del f 2 by del x 1, del f 2 by del x 2 all the way up to del f 2 by del x n. Okay. Like this, the last row, the nth row. Okay. So, this was your first row, this is your second row. The nth row will be del f n by del x 1, del f n by del x 2 all the way up to del f n by del x n, evaluated at x equal to x 0. Okay. So, once you know this tangent matrix, okay, you can set up the Newton-Raphson iterative procedure. Okay. So, how do you start? You have some initial guess, say we have some initial guess. So, here K, okay. So, we have some initial guess x 0, and then we want to find out the solution of our system of equation. So, what we will do? We will start with finding the tangent matrix at x 0, okay, and then using this equation number 46, we will find out the increment u. Okay. Now, because k was 0, okay, so k was 0, so x 1 will be x 0 plus u. Now, once you have x 1, you can recompute the tangent matrix at x 1, you can recompute your given nonlinear algebraic equation at x 1, and you can then recompute u, and then you can get x 2 as x 1 plus u. okay, and like this you will keep on doing, and there is certain stoppage criteria. Okay, we will see today, we will going to see the algorithm. Okay. The next one is the algorithm. Once a stopping criteria is met, you will say that that particular value of x where the stopping criteria is met is your solution. Okay. So, for the given second example that we have seen, this is the general algorithm for the Newton-Raphson procedure. Okay. So, it requires a number of steps to be performed in a certain way. So, we will look how we have to proceed if we want to find out the solution of a system of nonlinear algebraic equations. Okay. The first thing you have to input in your computer program is the function. Okay. So, your function has to be known. Okay. You know the function, okay, in terms of x1, x2 all the way up to xn. Okay. Now, you want to find out the solution. Okay. So, let us say you have some guess. Okay. So, let us say you have some initial guess x0. Okay. So, you can compute the value of the function at this point x0. Okay. So, you input your initial guess and then you compute the function, all the functions at this point. Okay. Now, let us say our solution will initialize to x0, okay, because right now we do not know the solution. So, we will say that let our initial guess be the solution and let the increment u be equal to 0. Okay. Now, we set the iteration counter. Iteration counter means the Newton-Raphson iteration counter to be 1. Okay. And also the maximum number of Newton-Raphson iteration that we want to do, okay, let us say it is n subscript max. Okay. So, this is also we need to define. Okay. So, this is essential because we do not want our Newton-Raphson iterations to go on indefinitely. Okay. At certain point, if the Newton-Raphson procedure does not result in our solution, then we will have to stop, because otherwise in computer it will keep on going. Okay. There are situations where Newton-Raphson will be stuck and it will not go anywhere. At that point, you have to do something extra. Okay. Toward the end of this course, we will see, okay, arc-length method and line search method. These are two techniques that you can use. Okay. But right now, we just set the maximum number of Newton-Raphson iteration, that is n max. And also, let us say we set a tolerance, okay, which is given by tol. Okay. Tolerance is, it is a use for a stopping criteria. Okay. When the value of the stopping criteria, okay, becomes less than this value tol, then we say that our Newton-Raphson iterations have converged. And then let us say we have, say, a residual value r, and this has to be set to a very large value as compared to our tolerance tol. Okay. So, normally you may set tolerance to be 10 raised to power minus 27, a very small number, or somebody might set 10 raised to power minus 6, it depends. Okay. You might set a very small number, or you may set like 10 raised to power minus 6, and then you may set r to be 10 raised to power 6. Okay. It is a very large number as compared to tolerance. Okay. Now, you start a loop, while loop, and you see whether your value of r is more than tolerance and the number of Newton-Raphson iterations is less than the maximum number of Newton-Raphson iterations. Okay. If both the criteria are met, then what you do? You go and compute your tangent matrix and the system of nonlinear expression, nonlinear algebraic equations at this point, okay, at x. And then you solve for u, and then you update x as x plus u. Remember, at n equal to 1, this x was x0, your initial guess. Okay. So, in a way, for n equal to 1, what you are doing? You are finding x1 as x0 plus u. Okay. Now, once you have evaluated the new value of x, you can recompute your function, and then what you can do? You can take the norm of the function, okay, divided by the norm of the function at initial guess. Okay. Now, this value of r, okay, if you are approaching correctly, will now become a small value. Okay. It is very unlikely that within the first Newton-Raphson iteration, this value of r will become less than tolerance, which is 10 raised to power minus 6, but in a way it will become a small value, say 10 raised to power minus 1. Okay. And then what you do, you increment the number of Newton-Raphson iteration, and because your r right now say is 10 raised to power minus 1, which is more than 10 raised to power minus 6, and also your n, say n max you set to be 50. So, n now is 2. Okay. So, now because 2 is less than 50, you go to next Newton-Raphson iteration. Okay. Now, again what you will do, you will compute k, the tangent matrix at x 1 and the force vector at x 1, you will recompute u, okay, and then what you will do, you will get x 2 as x 1 plus u, okay, and then again you check, compute the value of r and increment the iteration counter, and you keep on doing this, okay, till you come out of this do while loop. So, once you come out of this do while loop, which is step 6, your output will be, if the number of Newton-Raphson iterations are less than the maximum number of Newton-Raphson iteration that you had, then your solution will be x. Otherwise, you will say that your Newton-Raphson iteration did not converge. Okay. Once it did not converge, it does not mean that there was some problem. It might mean actually that there are some other issues, convergence issues, which you can go back and handle using arc length method, line search. Okay. All these kind of methods can be applied. Okay. But here for our second problem, for a given system of nonlinear algebraic equation, the following algorithm should work. Okay. So, with this general algorithm, we come to our second topic, which is tensor analysis. Okay. So, this is the last topic before we go to some worked out examples. Okay. So, till now what we have seen is our vectors or tensors were a quantity, okay, which was fixed in space. Now, we will have quantity which varies in space, that is, it is a field. Okay. We want to carry out certain operations on these fields. Okay. We will have scalar fields, we will have vector fields, we will have tensor fields. Scalar fields like temperature, vector fields like velocity, tensor fields like stress tensor. Okay. So, now the first quantity of our interest is gradient of a scalar field f in 3 dimension. So, we will restrict ourselves to 3 dimension, okay, and we want to compute the gradient of this scalar field f at point x 0 in the direction u, okay, and then we will do this in terms of the directional derivative. Okay. So, the gradient of a scalar field f at x 0 in the direction u is defined as, that is how it defines, okay, is defined as del f evaluated at x 0 dot u is nothing but the directional derivative of the scalar field f at x 0 in the direction u. Okay. So, what does it mean? Okay. So, equation number 48 will give you the change in scalar field at point x 0 in the direction of the vector u, and this is called the gradient of the function f at x 0. Okay. So, you know how to compute the directional derivative. Okay. So, this term over here, okay, this is here. So, the directional derivative of f at x 0 in the direction u will be d by d eta, eta at 0 evaluated at eta equal to 0 f of x 0 plus eta u. Okay. So, if you carry out as we did for the system of nonlinear equation, you will get equation number 49, which is summation from I equal to 1 to n del f by del x I evaluated at x 0 into u I. Okay. So, the first term is an ith term and the second term is also an ith term. Okay. So, you can see the gradient f at x 0 in the direction u is nothing but del f by del x I into u I. Okay. From this you can recognize, you can find out that del x 0 is nothing but del f by del x I E I, because this is nothing but say A I, this term, I can write this is a vector, this is A I into u I, which is nothing but vector A dotted with vector u, and comparing the left hand side with the right hand side, I can identify gradient of f at x 0 is nothing but this vector A. This vector A is nothing but del f by del x I evaluated at x 0. Okay. So, the gradient of f evaluated at point x 0 is nothing but del f by del x I E I, or for a generic point x, this can be expressed as gradient of f is nothing but del f by del x I E I, or in direct notation I can write del f by del vector x. Okay. So, more conveniently in indicial notation I can write this as f I comma j, and this is called the comma notation. Okay. So, you can see the gradient of a scalar field is in indicial notation is given by f I comma j, because there is a comma. Whenever there is a comma, it means the quantity before the comma is being differentiated with respect to the quantities after comma. In general, after comma it is always the position x. So, whenever you see say A I comma j, it means del A I by del x j. So, rather than writing this big expression, we can use the comma notation to shorten our expression. So, moving now from scalar to vector field. For example, let us say we have velocity field. So, vector field, for example, f at x 0 will be a second order tensor. If you had seen closely equation 51, the scalar field f was a something which was free of index, but now you have one index which comes. Sorry, this comma notation, this will be f comma I. So, you see you started with a scalar and you ended up with a vector. Similarly, when you start with a vector, you will end up with a quantity which is one order higher. So, after vector, vector has one index. So, we end up with a second order tensor which has two index, and gradient of a vector field f at x 0 is defined as the directional derivative of the vector field evaluated at x 0 in the direction u. And if we follow the procedure what is similar for the scalar field, we can show that the gradient of a vector field is nothing but double summation over I and j going from 1 to 3 del f I by del x j E I tensor product E j, or in direct notation we have del f by del x, and this incidentally is f I comma j. This is nothing but f I comma j. Now, one interesting thing to notice is if you take trace on both the sides of equation number 53. Now, if you take the trace on both the sides, what do you find? You find that so trace of gradient of a vector is nothing but divergence of the vector. Okay. This is a identity that we use. So, trace of gradient of the vector field, okay, f is nothing but trace of del f by del x. Okay. So, trace of gradient is nothing but divergence, and this is nothing but gradient of f, okay, into double contracted with the second order identity tensor, and in direct notation, okay, this is divergence of f, and in indicial notation you have f I comma I. Okay. So, in comma notation you have f I comma I. So, divergence of a vector field is f I comma I or any one of these mentioned over here. Okay. So, equation number 54 will be used later on when we go to our constitutive relations. Okay. It will be used a lot. Next, we move to the gradient of a tensor field. Okay. So, now we have a tensor field, for example, stress. Okay. Stress is a tensor field, it is varying over the entire domain of the body. Stress occurs in the entire domain of the body. So, it is a field. Okay. So, now how do you take the gradient of a tensor field? Okay. So, gradient of a tensor field will be a third order tensor. Okay. So, it is defined as this gradient of a tensor field A evaluated at x 0, okay, in the direction u is directional derivative of tensor field A evaluated at x 0 in the direction u. Okay. So, you can show that gradient of A is given by this expression over here. Okay. So, now there are 3 base vectors. So, it is a third order tensor. Okay. In direct notation you have del A by del x, or in indicial notation you have A I j comma k, that is your comma notation. Okay. Now, you can take the trace on both the sides as you did for vector field, and you can show that divergence of a tensor field is gradient of the tensor field contracted with the second order tensor, okay, or in indicial notation this is A I j comma j. Okay. So, if you have to take example divergence of stress, stress is a second order tensor, this will be nothing but sigma I j comma j. Okay. That is your comma notation. So, the last point to see is the integral theorems. Okay. So, now in many of the derivations in continuum mechanics, we have to deal with quantities which are integrated over the domain, okay, domain of the body or the volume of the body, and you have to relate them to the integral of the quantity over the surface. Okay. So, how do you do that? So, now consider you have this body as shown over here. Okay. So, you have a body B and the surface of the body is denoted by del B. Okay. Now, consider you have a scalar field F which is distributed over the volume B, okay, maybe like a temperature. Temperature will be distributed over the body, different points of the body may have different temperatures. Okay. So, you have, let's say for example, the temperature field. Now, you want to compute the integral of the gradient of the scalar field over the volume, okay, and this will be equal to the integral over the surface of the scalar field multiplied by normal to a point on the surface, okay, and then integrated over the entire surface, okay, where n is the normal to this infinitesimal area dA. Okay. So, what you do? You just, if you want to compute the gradient of the scalar field over the entire volume of the body, okay, then this will be same as the integral of the scalar field multiplied by the normal, okay, to a infinitesimal area dA integrated over the entire area of the body. Okay. So, now we can extend this to vector field f, and equation 58 then becomes what is shown here in equation 59. So, the gradient of a vector field integrated over the entire volume of the body will be equal to the vector field tensor product normal to the infinitesimal area dA integrated over the entire area, okay, of which is bounding this volume B. Okay. Now, if we take the trace on both the sides, if you take the trace on both the sides, okay, if you take trace on both the sides, what do you get? Trace of gradient of f is nothing but divergence of f. Okay. So, integral of divergence of f over the entire volume, okay, will be nothing but trace of f tensor product n, and using this property the trace of A tensor product B is nothing but A dot B. So, we will have integral over the surface f dot n dA, and this is nothing but the celebrated Gauss divergence theorem. This will be used very extensively in our coming lectures. So, you need to always remember this theorem, that divergence of a vector field over a volume integrated over a volume will be equal to the vector field dotted with n integrated over the entire area. Okay. Now, we can extend this to second order tensor. Okay. So, instead of a vector field, now if you have a second order tensor field A, then what do you get? The gradient of the tensor field A integrated over the entire volume will be A tensor product n integrated over the entire surface. Okay. Now, again if you take the trace on both the sides, you will get divergence of A integrated over the entire volume will be equal to A n integrated over the entire surface. Okay. So, that is how you can connect the volume integrals to the surface integrals. Okay. So, with this we have covered all the essential elements of tensors, okay. All the mathematical requirements for this course have been dealt with. So, next we will see some worked out examples. Okay. We will see how to take the directional derivative of determinant of a tensor, second order tensor, how to take the directional derivative of inverse of a tensor, and some other expressions, okay, before we move on to our next topic, which will be kinematics. So, next job is to move to worked out examples, that will look next. Okay.